Okay, so when solving limits, typically what we're going to get are indeterminate forms. It's very rare that you're going to use direct substitution method and it's going to work. Typically what's going to happen is you're going to get the indeterminate form 0 over 0. Okay. We could also get infinity over infinity, but I haven't spoken about limits at infinity or limits of functions which equal infinity. So I want to mention it because it's still an indeterminate form, but we're going to focus on the indeterminate form 0 over 0 specifically. So when you come across this, which most likely on a class test or an exam you will get 0 over 0, there's 4 typical methods that are used. So the first one is factoring. So if you're given a rational expression, a rational function, you may have to factor 2. If we have fractions, you might have to do some mathematical manipulation. If you're adding or subtracting fractions, you might have to find a common denominator. If you're dividing fractions, you might have to flip and multiply by the reciprocal, things like that. So you might have to do some sort of manipulation. 3, if you have a square root, you're thinking to multiply by the conjugate. And then 4, if you have an absolute value. You have to use the definition. Okay, so we're gonna take a look at all these cases here and work on some examples. So let's begin with factoring. We actually saw the example the last one we looked at was a factoring example. So let me erase this and rewrite the example. So factoring, we have the limit as x approaches 1 of, I believe it was x squared minus 1 over x minus 1. And we evaluated, we did direct substitution. So we should always begin limits by using the direct substitution property. So we substituted it, we got 1 squared minus 1 over 1 minus 1, which gave us 0 over 0. So we see it's an indeterminate form. Okay, fine. We have to factor, we have to use a different method. So in this case here, I'm thinking to factor because we have a binomial with a subtraction in between it. So you should be comfortable with your Sec 5 factoring methods. Whenever you have a binomial separated by a minus, this is difference of squares. So you have the property a squared minus b squared equals a minus b times a plus b. Okay, so when you have a binomial, when you have 2 terms with a minus in between, you should be looking out for this property. So instead of doing this, we could rewrite the limit as x approaches 1. So we're going to factor the top and rewrite it as x minus 1 and x plus 1. All that over x minus 1. And what you have to notice is that the denominator, x minus 1's cancel, leaving us with just the numerator. Limit as x approaches 1 of x plus 1. And now we could apply the direct substitution because we don't have a fraction, we won't get 0 over 0. So we're replacing your x with 1, we're going to get 1 plus 1, which is 2. And that's the answer to the limit of this function. Okay. Let's take a look at another example. Okay, so in this example here, we have the limit. We're asked to evaluate the limit. Limit as x approaches 3 of x squared minus 3x divided by x squared plus x minus 12. Again, we tried the direct substitution method. We substitute the 3, but what we get is 9 minus 9, which is 0 on top, and on the bottom 9 plus 3 is 12, minus 12 is 0, so we have the indeterminate form 0 over 0. So if we get a value, we stop, we're done, but 90% of the time or 95% of the time we're going to get infinity 0 over 0 or some sort of indeterminate form. So we have to move on and try factoring. So our first method, we have a rational expression. Let's try factoring. So if we look at the numerator, we have x squared minus 3x. We have a binomial, we have a minus in between. Could we use difference of squares? In this case, difference of squares does not work, because if you try to square root the x squared, that works, because x times x is x squared. So you are able to square root this term. But the second term, you cannot take the square root of 3x and give to get a value. So difference of squares I wouldn't use in this case. So I would try just GCF, greatest common factor. What's the most we could factor out from the numerator? And in this case here, we could factor out an x. So we have the limit as x approaches 3. We factor out an x and we're left with x minus 3. Okay. And on the bottom, we have 3 terms. We have x squared plus x minus 12. So when you have 3 terms, our factoring technique is the product sum method, or what some teachers call M&N method. So product sum method, let's do this on the side. I'm going to do it in red. Product sum. What you have is, it stems from the form ax squared plus bx plus c. So you typically have a quadratic when you're using this, where you have 3 terms. It doesn't necessarily have to be quadratic, but typically it's quadratic. The term in front of your x squared is your a, the term in front of your x is b, your term in front of your c is the constant that's on its own. So in our specific case here, the x squared plus x minus 12, what you have to catch is that your a is 1, your b is 1, and your c is equal to negative 12. So if you're not comfortable with product sum method, then you should take the time to actually write this out. If not, you could skip this step. But the idea is you're playing the game that 2 numbers that you multiply, you're trying to find 2 numbers that multiply to give you a times c, and those same 2 numbers that add to give us your b. In this case here, our a times c is 1 times negative 12. So we're looking for 2 numbers that multiply to give us negative 12, and the same 2 numbers that add to give us a 1, because b is equal to 1. So to save on time, because this could take a lot of time, especially if you don't have a calculator, it's difficult to do. So my advice to you is to look at the number here that you get from a times c. Ignore the sign for 2 seconds. Do not consider the negative. Just write down the factors of 12. This limits our options. So the factors of 12 are 1 times 12, so 1 and 12, 2 times 6, and 3 times 4. These are the pairs of numbers that we're going to be working with. 1, 12, 2, 6, 3, and 4. And now you have to ask yourself, now you have to consider the negative side. Which 2 numbers could you add or subtract from our pairs to give a 1? Well, 12 and 1, that's off by 11, or 13, that's too much. 2 and 6, that's off by too much, but 4 and 3 is the difference of 1. So the numbers we're working with are 4 and 3. Okay. So 3 and 4, 3 and 4. Now we have to worry about the sign. What 2 numbers can we multiply to get negative 12? One of them has to be negative. Well, since this answer here is positive 1, that means the bigger number has to be positive. So the negative goes on the smaller number. So the factors of x squared plus x minus 12 are negative 3 and 4. So we could rewrite x squared plus x minus 12 as x minus 3, that's the first root, and then the second root is 4, x plus 4. And now that's factored. This is work you do on the side. You could skip a lot of these steps, you don't have to spend this much time. But with practice, you guys should be comfortable with this. So here we get x minus 3 times x plus 4. This works out great because, again, now that we factored, notice the x minus 3 cancel, leaving us with, oops, I forgot my equal sign, leaving us with the limit as x approaches 3 of x over x plus 4. And now we could reevaluate the limit. And a trick to keep in mind, and this always works, whenever you have the factoring technique, look at the limit. The limit is x approaches 3. And look at what's canceling. A negative 3. Because essentially the reason why we're getting 0 over 0 is because we have a 3 over here, which is 3 minus 3, which gives us the 0. So essentially whatever the limit, as x tends to that value, the opposite sign is what's going to cancel when you're factoring. So that's what you should look for when you're trying to cancel out the terms. So the previous example that we had was the limit as x approaches 1. Notice that an x minus 1 canceled on the top and the bottom. So this is a trick that you could use just to make sure you have the right value, so you know, just in case you made a mistake over here, you could catch that by using this trick, because it always works. So lastly, let's evaluate the limit. Replace x with 3, we get 3 on top, on the bottom we get 7, and that's the answer. That's the limit of this this example. So that was an example with factoring. Let's take, we'll have all different types of factoring techniques, so you should be comfortable with all of them. Let's move on and look at an example with mathematical manipulation. So now we're going to look at an example with mathematical manipulation. In the previous example, we had a rational function, but now what we have is 1 over x minus 1/3 over x over 3. Sorry, x minus 3. And we're taking the limit as x tends to 3. So once again, we don't have a rational expression, not necessarily. It's not in the form yet. We have to manipulate it to get it in the form. So, but always the first thing we should attempt is direct substitution. If we replace our 3 into the function, we get 1 over 3 minus 1 over 3. So on top we get 0. And on the bottom we get 0. But this is in an indeterminate form, so it doesn't help. We have to keep evaluating. So this is always the first thing you should try, because if you do get a value again, you stop, you're done, the limit's done. In this case here, what we have to do is a mathematical manipulation. In this case, if we focus on the numerator, we have a fraction minus a fraction. So what you have to do is find a common denominator. So the property that we're using is a over b plus minus c over d. This always works. Is equal to a times d. So you multiply this way, you multiply this way, plus minus c times b, all that over bd. So this property here would always work whenever you're adding or subtracting fractions. Or at the same time, you can do like in high school. I don't know how you guys learned it, but here you have to match the bases. So here you're missing a 3, so you multiply the top and the bottom by 3. Here you multiply the top and the bottom by x, and then we have the same denominator. So both methods are fine. So in this case here, limit as x approaches 3, we have 3 minus x over 3x divided by x minus 3. Okay. So using this property, we get this. The way you should be thinking of it is, on the top we have a fraction, on the bottom technically we could think of it as a fraction. We have a fraction divided by a fraction. This is like a large division. Okay. So whenever you have a fraction divided by a fraction, this is done often, you multiply by the reciprocal. So the same as if you have a half divided by 3/4, the way you would do this is 1/2 times the second fraction flips, becomes 4 over 3. Okay. We're doing the exact same thing here. So you're taking the limit as x approaches 3. The first fraction stays, so 3 minus x over 3x. But now we're going to multiply. Instead of x minus 3 over 1, we're going to flip the second fraction. We're multiplying by the reciprocal times 1 over x minus 3. Okay. And this is easier to work with. Let's remove this. Next, what you're going to do is 3 minus x and x minus 3 is very similar. They're very close, but what you have to catch is it's off. They're basically in the reversed order. So what you can do to remedy that, and this is a common trick, you factor out a negative. So we could think of the numerator as -1 times x minus 3. If you are not convinced, what you should do is multiply back the -1 and see if you get back what you started with. And on the bottom we can multiply these guys, but don't like leave them in factored form. Like do not distribute the 3x, because then you're going to lose the fact that these guys cancel. So the same trick that we saw earlier, limit as x approaches 3. Since it's 3, what do we know? We know, or we expect, an opposite sign of 3 is -3. We expect an x minus 3 to cancel, as it does. Okay, so keep that in mind. That's a good trick. And what we're left with is the limit as x approaches 3. -1 on top, 3 times x. Substitute the x in now, we get -1 over 3 times 3 is 9. And this is the answer. Okay. So this is an example of mathematical manipulation. Let's take a look at an example with square roots. Okay, so in this example here we have square roots involved. So again, we always begin by evaluating the limit, direct substitution. Substituting x with 0, what we get is 0 plus 3, square root of 3 minus square root of 3 is 0. On the bottom we have 0. So this gives the indeterminate form 0 over 0. That doesn't help. So we have to keep evaluating. The way we keep evaluating, whenever you have square roots, your first instinct should be to multiply by the conjugate. So this should be a reminder, you should have seen this last year. Multiplying by the conjugate, what you're doing is it's a fancy way of multiplying by 1. You're not altering the function, you're just multiplying it by exactly what you have here in the numerator, whatever you have in the square roots, everything stays. You only switch the sign. So you're going to multiply by the square root of x plus 3, but instead of minus square root of 3, it's going to be plus square root of 3. So inside the root, the sign stays, but in between the two terms, you switch the sign. Okay. And you do that to the top and the bottom. X plus 3 plus square root of 3. Notice that what's in red here, it's the same thing. So dividing anything by itself is 1. except when we're dealing with infinity or zeros. But any number divided by itself is 1. And now we're going to evaluate. So to evaluate this, what we're going to do is on the top, we're going to distribute. Okay, we're going to use FOIL. On the bottom, there's an x times these two terms. Do not distribute. So this is a common mistake that students were making. They would distribute and then they would lose their form. Leave it as is. Just deal with the numerator. So we have the limit as x approaches 0. Distributing the first term, I'm just going to write it quickly. We have x plus 3 times square root of x plus 3. I'm going to write it all out. You don't have to do it this way. I'm just going to show you for the first time. This times this. Next it's plus square root of 3 times square root of x plus 3. Then minus square root of 3 times square root of x plus 3. And then lastly minus square root of 3 times square root of 3. All this over, I'm going to leave the x times square root of x plus 3 plus square root of 3. We're going to leave it in this form. Okay. This is long. After you're comfortable with, you can start skipping steps. The property that we're using here is the fact that the square root of x times the square root of x is equal to just x. If you're multiplying the root of two terms which have the same, let's say the same base, the answer is just what's inside. Another way of thinking of this is that x to the square root is the same thing as x to the half times x to the 1/2. We could rewrite square root as exponent 1/2, and when you're multiplying the same base, x times x, you're adding the exponent. A half times a half, a half plus a half is a whole. So x to the 1. That's what we're using. We're using these properties here. So we have the square root of x plus 3 times the square root of x plus 3. What's inside the root is the same. So we're left with just, in this case here, x plus 3. Limit as x goes to 0. So notice that I'm always writing equals and then limit. Don't forget to do that. We have x plus 3. Now, the purpose of doing the multiplying by the conjugate is these two middle terms here are always going to cancel. If they don't cancel, you made a mistake, go back and check, but it's always going to work out for these two terms to cancel. We're essentially using difference squares backwards. So this is always going to happen. So we have plus square root of 3 times square root of x plus 3 minus square root of 3 times square root of x plus 3. So same numbers, opposite signs, cancel, and what we're left with here is minus square root of 3 times square root of 3. Same argument here, since the roots are the same, the numbers are inside are the same, the answer is just 3, so we get just minus 3. And then we're left with x in brackets square root of x plus 3 plus square root of 3. So as I mentioned earlier, leave the x on the outside. Our trick here, it still works, because if we have x which is tending towards 0, well, then what's going to cancel? Well, we change the sign of the x. It's going to be x minus 0, which is just x. So we expect, since the limit as x approaches 0, gave us 0 over 0 when we direct substitute in the beginning. Notice that we're expecting an x to cancel using our trick, and it does, because here we have positive 3 minus 3. These guys cancel. So on top we're left with x. On the bottom we have the x that we left out. Do not distribute it because you might lose it or you might not see it after. But this x here cancels with this x, leaving us with the limit as x approaches 0. On top, since the x's here cancel, on top we're left with 1. Don't forget that, it's not 0. And we're left with x plus 3 plus root 3. Now if we evaluate the limit, we're replacing the x with 0. So what we get is 1 over root 3 plus root 3, because 0 plus 3 is root 3 inside the root. And we're left with 1 over 2 root 3. And this is the final answer. Okay. So this is an example with square roots where we multiply by the conjugate. Very typical. The next example that we're going to look at is going to be with absolute values. How do we deal with absolute values? Okay, so in order to evaluate the limit when we're dealing with absolute values, we need to know the definition of an absolute value. So by definition, the absolute value tells us that if we have absolute value of x, it's going to split into two cases. It's going to stay as x if x is greater or equal to 0, and it's going to become negative if x is negative. Okay, so this needs to be memorized. Okay. Think of the absolute value function. It's essentially at v, a v that passes through the origin. this is the y-axis, this is the x-axis. Okay. So it's supposed to be a straight line, but essentially here we don't want any negative values, so the negative side is flipped and turns positive. That's what this is telling us. Okay. So using this definition here, how do we apply it into the limit? So first things first, we always direct substitute to see, hopefully we don't get 0 over 0 or an indeterminate form. But replacing 6 into the limit, we get 3 times 6 minus 18. 18 minus 18 on top, we get 0. And on top, 6 minus 6 is 0. So we still have the indeterminate form, that didn't help. But let's split it up using our definition. So we could rewrite this as the limit as x approaches 6 I'm going to put it in the bracket. And here it's saying essentially to take whatever's in the absolute value and place it here. So what's in the absolute value? We have our 3x minus 18 over x minus 6. Okay. And we're going to use this over here. So we essentially just take out the absolute values. And it says if whatever's in the absolute value is greater or equal to 0. So here what's in the absolute value is 3x minus 18. Has to be greater or equal to 0. Okay. We use the same argument for the bottom. It splits off. Whatever's in the absolute value, essentially we put it in brackets and put a negative in front. So I'm just going to rewrite the limit as x approaches 6. Oops. And we're going to remove the absolute values and we're going to put negatives in front. So 3x minus 18, put a negative in front over the x minus 6. And we're going to use it if whatever is in absolute value is less than 0. So what's in the absolute value? The 3x minus 18 is less than 0. Okay, so now let's simplify this. So on the top we have the limit as x approaches 6. And here notice that we can factor out a 3. So by factoring out a 3, we have x minus 6 over x minus 6. And as expected, since the limit is approaching 6, we expected a minus 6 and x minus 6 to cancel, so our trick still holds. If here we could solve for x, so we'll move the negative 18 over, it becomes positive 18, and then divide both sides by 3. Be careful, we're working with inequalities, so if you divide by a negative or you multiply by a negative, the inequality sign flips. So this becomes 3x is greater than 18, divide by 3. This applies for x greater or equal to 6. And then we have the limit as x approaches 6. Actually, I'm not a fan of the notation, so I think I'm just gonna remove the limits. Okay, and focus just on the function. So let me rewrite that. All this holds, all this holds, and we'll just sit the limit in the front. Okay. And we do the same thing on the bottom. We factor out a 3, so we're left with negative 3 on the bottom. We're left with x minus 6 on the numerator and x minus 6 on the denominator, which cancel if x is smaller than 6. Okay. So since we're looking for the limit as x approaches 6, what we have here is, okay, I'm not a fan of the notation that I'm using, but essentially if we graph this, what we have is the y value is 3 for x greater or equal to 6. So at 6, we have 3 and negative 3. So at 6, when x is 6, bigger than 6 or equal to 6, the limit is 3. But for smaller than 6, when your x value is smaller than 6, it's negative 3. So something that looks like this. This is at negative 3. Okay. So we want to know what the limit is at 6 as x approaches 6. But notice that when we take the limit as x approaches 6 from the left side for smaller than 6, so slightly to the left of it, of this function here, I'm just going to call it f of x. The value of our limit is equal to -3. Yet when we take the limit as x approaches 6 from the positive side, so a bit to the right of 6 of this function here, the value of the limit is +3. So the left limit is -3, the right limit is +3. What can we say about the limit at 6? So this is from an earlier video. In order for the limit to exist, the left-sided limit and the right-sided limit has to match. In this case, the left-sided limit and the right-sided limit do not match. Therefore, the limit as x approaches 6 of the absolute value of 3x minus 18 over x minus 6 does not exist. Okay. Because the left-sided limit and the right-sided limit do not match.